Everybody can see that, I hope. Hi, everybody. I'm Mark Feit. I work for Internet 2. I'm also a member of the perfSONAR development team. And this is kind of less a technical deep dive and just more sort of a general talk on measurement and how to do measurement in rented infrastructure. So we're going to cover a little logistical problems there. We're going to cover three things today. We're going to talk about the fundamentals of measurement. We're going to talk about the cloud business model and how it affects measurement. And we'll spend some time talking about how to deal with measurement in uncertain environments. Time is a little tight on this presentation, so I would ask that you try to hold questions toward the end. There is a break afterward. And additionally, I'll be around for about an hour in the breakout rooms after we conclude this afternoon. So let's dive right in and let's talk about measurement. A lot of these presentations tend to have a what is slide, and this one, of course, is going to be no exception. So I stole a definition from the Encyclopedia Britannica that defines measurement as the process of associating numbers with physical quantities and phenomena. Now, of course, we are people who measure networks, and networks are sort of more logical things, but I think that definition fits pretty well. When you do measurement, you might be measuring, for example, if you're in the business of making dinner plates, you might be interested in the diameter of the dinner plate. You might be interested in the temperature of the air around you, or how fast you can get a signal through a cable, or how many bits you can push through your network in a certain amount of time. Now, one really important question is why measure anything at all? And the reason you do that is so that you can set expectations. If I can go back to the dinner plate example, if you're manufacturing dinner plates and maybe you make the first few and you decide that a diameter of 230 millimeters is okay, and maybe you set a tolerance of plus or minus 3 millimeters, that sort of defines your acceptable dinner plate and gives you a benchmark to work against. You'd continue doing measurements to make sure that your expectations are being met. So if you pull a plate off the line and it comes off with a diameter of 229 millimeters, that's okay. It's within the tolerance. Ship it. On the other hand, if you pull a plate off that's 234 millimeters, that's not okay. And that is something that you want to avoid doing because it's not what your customers are expecting. So in between those two events, though, you can use measurement to identify trends toward your expectations not being met. So, for example, if you're usually pulling dinner plates off the line every so often, and they're 231 millimeters across, and you start seeing 232, 233, that gives you an indication that it might be time to start checking the equipment and making sure that you're not going to start producing things that your customers aren't going to want. Measurements have two parts. The first is the measurement system. That's the thing doing the measuring. And the second part is the subject of the measurement. Industry has a whole lot of terms for that. You'll hear terms like device under test or network under test. I'm just going to use system under test because I think that's sufficiently generic for these purposes. I do have a rule about measurement that says that the best measurements come from having complete control over your measurement system. Rules, unfortunately, are never really hard and fast and were occasionally meant to be broken. So I have to amend that a little bit and say that if you don't control the measurement system, you at least have to understand it. And if you don't understand it, you at least have to trust it. Now, what does all that mean? To begin with, you have to understand what your measurement system can and cannot do. For example, if you have a 100 gigabit per second network and you're trying to test it with a Raspberry Pi, that's not likely to get you the kind of throughput measurements that you'd be looking for. So you have to make sure that you're using something that's capable of doing what you want. You also have to understand how precise and how accurate the measurements are. Now, precision and accuracy are two different things. Precision is where you can say, I have 5 places to the right of the decimal point. And accuracy is where you can say, yes, those 5 places are all correct, and as is the thing to the left of the decimal point. So even if you have 5 places and what's to the left of the decimal point is way off, then your measurements are kind of meaningless. You also need to understand what factors can have an impact on what the results are. For example, perfSONAR gets run on a general purpose computer, and if you're doing things other than measurement on that computer at the same time, some of those things can cause contention for resources that will distort the results that you get for them. And finally, under the heading of trusting your measurement system, if you're not in a position, and this applies to things other than just perfSONAR, if you're not in a position to understand how it works, you at least have to trust a third party who does. So that's an important thing to look for as well. So finally, under the heading of amending this once more, really, if you don't have understanding of your measurement system or any trust of it, you're not necessarily going to get meaningful measurements. And meaningful measurements are really important, and without them, you really have no path to making good decisions. So that's why all the understanding and so forth is important. When you don't have understanding, it tends to create a lot of uncertainty. One of the questions that we get asked a lot is, why is it that latency measurements over short distances produce negative results? Now, normally I like to tell people that it's part of some awesome new piece of perfSONAR time travel technology where we figured out how to get the packets to arrive before they departed. But the real answer is actually a lot more mundane than that. And that's just that the clock discipline is inadequate for doing that kind of measurement over such a short distance. Additionally, you have to understand the measurements themselves. You have to understand what it is that you're measuring, and you have to understand what that measurement means to the system that you're measuring or trying to adjust so that the measurements come in as you want them. And you also have to understand where the measurement system ends and where the system under test begins. So I'm going to take a little bit of a left turn, and I'm going to talk about this rather expensive looking device, which is called a vector network analyzer. Now, this is a piece of test equipment that's used in electrical engineering to measure a whole bunch of amplitude and phase characteristics of a class of electrical circuits that are known as two-port networks. Now, if amplitude and phase sound maybe just a little like throughput and latency, you're kind of not that far off. And if two-port networks sound like taking a network and putting a perfSONAR node at either end and making measurements, you're not far off with that either. The reason I bring this thing up, though, is that one of the things that this instrument includes when you buy one is this neat little box here that you see highlighted by the arrow. It's called a calibration unit. And it has in it a whole bunch of electrical circuits with well-known characteristics. And the instrument can use that to calibrate out the effects of things like the big black cable that you see and the connectors, which at RF, which is where this instrument operates, is actually fairly important. And what it means is that once you've been through the calibration procedure, and if everything is working properly, then the instrument will be able to tell you exactly what the circuit that you actually plug in there to test is doing. And of course, this being an analog gadget, you have to send it out to a lab and make sure it's calibrated by a lab that you can trust that will put it into the right place. The reason I bring this up is that even with networks, it's very important to calibrate before you measure. One thing that you cannot do is try to vet your measurement system across the system under test, because it's going to cause all sorts of problems. If you start to see measurements that indicate a fault, you kind of end up scratching your head and wondering whether the problem was that the measurement system was not fully capable of doing measuring what you're measuring, or whether there's actually a problem in the system under test. So what I strongly recommend is setting your measurement system expectations in the lab first before you put them out in the field. Doing that removes as many variables as possible. So as an example, at Internet 2, we have a couple of machines in the lab that are being vetted to be put out in all 47 of our POPs. And what we have is we have two of them sitting basically next to each other in a rack in the lab, and they're connected by a piece of fiber. So there's no switches, no routers, no nothing between them. And that lets us figure out whether or not the measurement system is capable of doing what we want without having to put a real functioning network with all the vagaries that kind of come with that in the middle of it. One thing that we can do, and you can do this as well, is you can simulate problems like high latency or throughput bottlenecks using equipment that you trust and control. And that way you have a sort of a better feel for whether or not the measurement system is doing what you want. So having covered all that, let's talk about the cloud and its business model. Now, in the beginning, and when I say the beginning here, I mean the late 60s or the early 70s, somebody bought a computer and started selling time on it. And this was called time sharing. And they kept doing that until the computer ran out of unused time. So they bought another computer and started selling time on that. And that computer eventually ran out of time. They bought a third computer. You can sort of see where this is going. In 50 years, not a whole lot has really changed. Only the units have gotten bigger. Where you started with computers, then you had racks full of computers and aisles full of racks and floors and data centers and zones and regions and planets and whatever other unit what's become the cloud providers can come up with. Now, for them, this is great. They get huge economies of scale out of this. They can buy lots of identical computers. They can set them up the same way, manage them centrally, occupy as much of their time as possible with paid work, and that's how they make money. Now, in a lot of ways, in addition to being good for the cloud providers, it's also really not bad for the consumers either, especially where you have scientific or HPC type workloads, because there are lots of compute cycles available to spin up on demand. So you can, when you need them, you can grab them, you do your computation. Once you're finished, you press the button and they all go away. You don't have to worry about boxing them up or pulling them out of racks or anything else like that. And it doesn't cost a whole lot to do. Unfortunately, where the large print giveth, the small print taketh away. And what you trade off for the cost of this, for the low cost, is that you actually have relatively little control over where these instances are located. So if you spun up an instance 5 minutes ago and you spun one up now, you have no idea whether it's going to be in the same rack, the same aisle, the same building, or even the same city as the previous one. So what that means is that if you take measurements on an instance, they're really only valid for that instance at that time. Further, a lot of these machines are shared, which means you're competing with other users of the same system for resources. You can, of course, get guaranteed resources like CPU, memory, and storage, but it tends to cost more. Networking, which is sort of where our concern is tends to be, in a lot of ways, best effort. You do get an SLA for uptime, but not necessarily for performance. Fortunately, for better or for worse, there tend to be high bandwidth, low latency links to vendors' other services, but not necessarily the outside. And the reason for that, of course, is that they have a lot of control over what they do internally, but none over networks that they peer with. So that's really sort of the limits to how much they can guarantee. So what you end up with is this continuum of cost versus control, where on the one side you have things that cost less and give you less control, and things on the right side where you have things that cost you more and give you more control. So, for example, you can ship a package FedEx ground. You give them your money, you give them your package, and it disappears for a while and it pops out on the other end. On the other hand, if you have a really important package and a lot of money, you can ship FedEx Custom Critical, where they will put your package on a dedicated truck, excuse me, and ship it out to its destination. If you give them even more money, they'll have somebody who's bonded and insured sit and babysit it the whole trip. Same deal with cars. You can go to BMW dealer, buy a 3 Series. You sort of get limited options and limited colors. Or you can go up the street to sister company Rolls-Royce and talk to their bespoke people. And as long as you keep pouring money into them, they'll build pretty much anything you want. Compute's actually no different. The things that you get in the cloud are sort of cookie cutter, but they're cheap. On the other hand, if you want things that are done custom or to your specifications, on-prem is more expensive, but it tends to cost a lot more to do. Now, custom measurement inside of a cloud provider is kind of difficult, and I'm reasonably sure that this conversation has probably been had 3 or 4 times with 3 or 4 of the cloud providers, where you go to them and you say, hey, we'd like you to install a perfSONAR node on your side of our peering. And the cloud provider may scratch their heads a little bit and stare at you for a minute and start asking questions like, are you already sending us a very large amount of money? And if the answer to that is no, they're probably going to ask, would you be willing to send a lot of money their way? And if you say no to that, they're going to say, well, we have this high economy deployment model, and what you're proposing would not make us a whole lot of money, so thanks, we'll pass on it. Now, the reason for this, there's a lot of reasons actually. Most customers actually don't care about this sort of thing. Scientific is sort of a different beast. If you're working a startup that's trying to do social networking for hamsters, that's sort of, in a lot of ways, is one of their big target markets, where huge amounts of performance are not really necessary, but it's really great to be able to have a lot of machinery without breaking the bank. Additionally, installing these kinds of measurement systems occupy space and power that could be used to generate revenue. And of course, the big cloud providers are fairly revenue sensitive. Doing proper instrumentation of the entire network would also be pretty expensive and very impractical. And as a side effect of that, providers would probably end up revealing a lot of information about their internal architectures that they'd rather not. So where does that leave us? You have, of course, your research backbone, and you have a cloud provider's network, and you probably have a peering with them. If you're doing something, if you're fairly typical R&E, you probably have a perfSONAR node that's plugged directly into your peering router. So at the very least, everything that's sort of to the left of that can test to there. Then, of course, you've got your actual peering. And while it would be really nice to have perfSONAR over there, unfortunately, you don't. And in a lot of ways, that kind of casts a dark cloud over things as far as doing good measurement and knowing how your peerings are functioning. So the next question is, and this has been asked, as I said, it's been asked a lot. How do you deal with this? We've been talking about doing this presentation probably for 4 or 5 years now. And we've spent a pretty good amount of time discussing it. And unfortunately, what we've come up with is that there's quite simply not a lot of good answers for this question. A lot of people have resorted to do-it-yourself measurement, where you spin up an instance, you install a measurement toolkit like perfSONAR and make a bunch of measurements. Unfortunately, interpreting the results can be a little iffy. To begin with, you have to measure many times, which is not necessarily cheap or easy. And really, all you can do with it is take a look at the mean or maybe the distribution of how the measurements fell out, and say, okay, on average, this is what we can expect from Cloud Code services. And just like anything else, of course, seeing a handful of really good results doesn't allow you to cherry pick those. And even if you do, it doesn't matter, because in a lot of cases, conditions may change anyway. Even if you do a lot of it, there's still a lot of uncertainty that comes with it. So you may spin these up one at a time, and you have no idea whether you've gotten 100 physical hosts once or 50 hosts twice, or the same host 100 times. If you're clever about it, try to spin everything up at once. Of course, you still have the same problem. You don't know if it's 50 hosts in clusters of 2 or 25 and 4 or other weird random arrangements. And really, because of the way this stuff is structured, topological diversity is really anybody's guess. Very early on, one provider started doing dedicated servers, and everybody was real excited about that until they figured out that they were at a completely separate data center in a completely separate part of the country, and the measurements they were making were not necessarily related to the computing that they were doing. There is configurable locality where you can start to say, I'd like this, regionally closer, but it's not anything new yet, and it still has the same set of problems. I think I'm starting to run out of time here, so let me blow through the rest of these real quick. So throughput seems to be really important to everyone, which kind of makes sense. I mean, you spin up an instance, the meter starts running. That meter continues running the whole time you get data in while you're doing your computing and getting data out as well. And mercifully, all this comes to a stop when you finally destroy the thing. But you really have two things that are sort of very cost uncertain, because you have no idea what the performance is going to look like, and that's the amount of time that you spend getting your data in and out. So I've done a little bit of thinking about perhaps how to optimize this stuff for cost, and I will say that I have not studied this extensively. It's sort of more a food for thought exercise. So you have a big blob of data that you want to do computations on. And my thought is that it might be better to transfer that data into your cloud provider's bulk storage first, because the time that it takes to transfer in doesn't matter. They don't start charging you for the storage until the objects have actually been written. And in the meantime, you don't have an idle compute instance burning cache. So after you do that, you start up your compute instance, you transfer the data in, and you get rid of it from bulk storage, and its existence ends, and that's the end of it. I think this might actually be a better approach. because throughput between bulk storage and compute is likely better because of physical proximity and more control over the infrastructure. And also because storage tends to cost less per unit of time than compute does. Typically, you're looking at 2.5 to 3 cents per terabyte per hour for storage, and really only the smallest compute instances are competitive with that. So I'll kind of blast through the rest of this, but basically you have some possible savings based on the fact that you're using your compute instances for less time while you're doing data transfer. So with that, I'll kind of wrap it up here. So the important highlights from this are just understand what your measurements are and your measurement systems and the environment where you're making them. The cloud is not a wonderful place to do measurement. A lot of people have been tearing their hair out about that for several years now. And there may be some ways, as I just discussed, to try and engineer your workloads to suit the environment and reduce your dependence on measurement as a way to control costs. There will be Q&A throughout the break. I'll be in my break room or my breakout room if you have questions or want to talk about anything. And having said that,